Hello, class. Welcome to lecture one in the series on college algebra. So today we're talking about equations and functions, which sound like scary words you've probably seen before, but hopefully we'll see that they're not so bad today. Okay, so start with equations. So in math, we often, for various reasons, study equations. And equations can be lots of fancy things, but for us, we want to start from the bottom. So we're just going to study equations which relate two variables. So just to remind you, variables, they're just letters that we use to represent potential numbers. And the two that we use pretty much always are x and y. So we study equations that relate the two variables, meaning that the two variables are involved in expressions on two sides of an equal sign. So something like this is an example of an equation, because an equation involving these two variables, because it's got both variables and it tells you a relationship between them. And the relationship is that if I do 2 times x plus 4 times y, that'll get me 9. And x and y can just be various numbers. And so this equation tells me how the potential numbers are related. So we'll go through it in more detail, but first let me write down some more examples. So then we can do fancier operations like squaring, which you may or may not remember. So remember, squaring means you multiply by itself. So I can have an equation that involves squaring in it, something like this. So this is now saying if I square the x variable, meaning I multiply it by itself, then I add y, that will add up to -7. I could have one variable on one side and the other on the other side with some other numbers and some other operations. So that's a cube power. So I multiply x by itself 3 times, then I make it negative. Then I don't know, add 2x squared. So I square x, multiply by 2, and then I add 5 or something. So these three are equations relating x and y. And then we make this sort of arbitrary choice. We call x the dependent variable. And that's because, sorry, the independent variable, whoops, almost a big error. The independent variable, because when we actually use these equations, what we're going to do is we're going to figure out which x's and y's obey them or solve them. And so what we do is we often choose x first. So we choose values of x. So when I say values, I just mean typical, I just mean numbers, possible numbers. We typically choose values for x first. So that's why it's independent. We can just choose whatever we want. And then y we figure out after we pick x. And so y is called the dependent variable. Hopefully I can spell these words right. Because we determine it. We determine values of y after x has been chosen. So what we do is we think of it as x. So i.e. x determines y because we're choosing it in this order. And so we should think of x as being independent and y dependent on x. That's why it's called the dependent variable. Okay, so there's a lot of sort of theory sounding stuff. So let's just do some examples to really see what's going on exactly here. It's not so bad as it seems. And this will happen a lot in this class. We'll see some stuff seem very hard, and the examples will make it a bit easier. So here's an example. If x equals 2, then the equation 3x plus y equals 5 determines the corresponding y. And how do we do that? So like I said at the beginning, an equation determines a relationship, relates to variables x and y. So what this is really saying is x and y come in sort of these pairs. If x equals something, then y has to equal a corresponding number to match with that x. And what we're going to do now is see an example of that. So how do we determine the corresponding value of y? All we do is people call it plugging in x equals 2. And what that really means is we're going to change all the x's in the equation into 2's. And then we can solve using algebra. Oops, how do you spell algebra? Algebra rules for y. Okay, so let's go ahead and do it. So I have 3x plus y equals 5. I'm changing my x's into 2's. So when you plug something in, you're often want to keep a parenthesis. You're often going to want to keep a parenthesis around it. It'll help make things more clear in terms of order of operations and what you should be doing. So the equation with 2 plugged in for x becomes this. And math notation is very delicate. You have to write things correctly or it will not make sense. So I'm being very specific with my equal signs, my plus, my multiplication, everything is very precise here. Do not try to make your own notation. Okay, how do we solve for y using algebra? Well, first I can multiply this 3 and this 2 together. That becomes 6. And to solve for y, I can simply subtract 6 from both sides because that cancels the 6 on the left and leaves y alone. And then I just have to remember how to subtract. 5 minus 6 is -1. So what this tells me is that the corresponding value of y is -1 for this x equals 2. Okay. So x equals 2 corresponds to y equals -1 for this equation. So we see that the equation is really what determines that these two go together. X is 2, y is -1. If I pick a different x, I'll get a different y. So if I pick, you could follow the whole thing the same way. You could do x equals 4 and say, well, what y corresponds to that? You just do the same process. 3 times 4 plus y equals 5. This becomes 12 plus y equals 5. Subtract 12 to the other side, and you get y equals -7. So -7 is the corresponding y value for this x value for this equation. So which x's go to which y's really depend on the equation. Okay. Let's see a different equation example. So for the equation, something a little bit fancier, x plus y squared. Apparently I'm ready to rent a book from the library. Okay. Sorry that popped up. Okay. For the equation x plus y squared equals 6, we get different relationships between x and y. X equals 5 will actually determine 2 values for y instead of just 1 like it did last time, where I used 3 and I got 1 value of y. This time I'll get 2 values of y. So let's see it the same way. So we get 5 plus y squared equals 6. You'll notice that I write a lot of words when I do the steps like this, and I think it helps keep things clear. And I would recommend doing it when you do it too, especially if you really need the practice. Okay, so anyway, to solve for y, I just need to subtract 5 from both sides. And that'll get me 1 there. And now there's actually 2 values of y that solve this equation. And that is y equals 1 or y equals -1. They both work because either one of them, if I square them, let me keep them in the same order, 1 squared equals 1, which means that y equals 1 solves the equation, but also -1 squared equals, if you remember what squaring means, it means -1 times -1 and multiply it by itself. A negative times a negative is a positive. So -1 also works as a solution to this little equation at the end here. And so we get that x equals 5 determines, with this equation, y equals 1 or y equals -1. So we want to keep thinking about it as x is determining y. X is the independent variable, and then y depends on x. So the y we get comes after we plug in an x, choice for x. And in this way, what we do is we really think about it as an equation creates, and we can call this an assignment or a mapping. Some people call it a mapping, or other people call it a relation. We're not going to need to remember these words too much. The point is it creates this assignment of x values, numbers that x can be, to y values, numbers that y can be. So for example, what we just did, 3x plus y equals 5 creates, and so the way we indicate this mapping or this assignment is we just draw a little x and a little y, and we think of it as x's are turning into y's. So we draw a little arrow there. And underneath, you just write which numbers are turning into which numbers. So I think we used 2. So let's just rewind a bit up here on this equation. Way up here, I'm using the same exact one. So our 2, x equals 2, we're now thinking of as turning into y equals -1. So we just draw a little arrow that says 2 is turning into -1 like that. And then we could do lots more examples. So just by plugging them in. So if I can use negative numbers for x, that's fine too. You can use whatever numbers work. 3 times -1 plus y equals 5. This will help us practice using negative numbers. 3 times -1 is -3. Now to solve for y, I have to add that 3 over. So I get 8 there. So this is saying that -1 is getting assigned to 8. So this is sort of how we visualize the assignment in sort of chart type form. And you can verify this one on your own. If you do 5, I believe you'll get y equals 10. So, or sorry, y equals -10. So I'll leave that one to you. But that would mean over here that 5 becomes -10, and you would write it like that. And of course, these are not all the numbers in the world, among many more. So this chart would go on forever if you just kept putting more numbers in. And you could also put in fancier numbers like fractions, numbers between numbers, things like that, instead of just these whole numbers that we're doing. But we don't want to deal with all those things for now. Okay. So this is what I mean by an assignment. And then after we have an equation which creates an assignment, we can visualize it even better. So we can visualize this. 1 second. Okay. We can visualize this assignment by drawing the graph of the equation. So if you have an equation, it has an it creates an assignment, and it also creates a graph. So what is the graph of the equation? Well, it's all, so consisting of all the x, y coordinates, or let me call them points. All the x, y points, we'll call them coordinates too. I guess I'll leave that too. On the xy plane. So the xy plane, you may not remember, but I'll review it in a second. So it's all the xy coordinates on the plane that come from doing the equation. So where the xy satisfies the equation. So we can go ahead and use our example that we just created right here. So the graph of this equation, let's look at that. Okay, so the graph of this equation must have points that come from using the equation. So right now what we know is that, for example, x equals 2 gets assigned to y equals -1, if I remember right. X equals -1 got turned into y equals 8. And x equals 5 got turned into y equals -10. So all I'm doing is sort of rewriting that chart in a different way. But what that really meant was plugging in x equals 2 got me y equals -1, plugging in x equals -1 got me y equals 8, and so on like that. So the graph has points corresponding to each of these things. So what are the points? The points will be 2, -1, because x equals 2 corresponds to y equals -1. It will have the point -1, 8, because x equals -1 corresponded to y equals 8. And it will have 5, -10, because x equals 5 corresponded to y equals 10. So it has these 3 points on it. That doesn't mean that these are all the points because, like I said up here, these are not all the relationships that are created by the assignment. 2 is related to -1, -1 is related to 8, 5 is related to -10. There's so many more, but these are 3 of them. So we can graph these 3 points on the xy plane. And oftentimes this helps us visualize how the graph might look. Okay, so remember that the horizontal axis is the x-axis and the vertical axis is the y-axis. That's why it's called the xy plane. And so if I want to graph the point 2, -1, I have to go left and right 2. So I have to go right 2. And then that's because to the right is positive and to the left is negative. And then for up and down, that's where my y coordinate comes in. Up is positive, down is negative. So 2, -1, I go over to the right 2, then I go down 1, and that tells me 2, -1. That's a point on the graph. I could do -1, 8. It's gonna be a tough squeeze. 1, 2, 3, 4, 5, 6, 7, 8, something like that. That would be sorry. That's the next one. -1, 8 is also on the graph. And then 5, 5 down 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The beauty of it is if you just label it, nobody will question if you counted correctly. So just label it what it's supposed to be. Okay. So I've graphed these 3 points. They are on the graph. That doesn't mean that this is the graph. I've just graphed 3 points. So this is just 3 points on the graph, but not the whole graph, just to keep that very clear. That's all we're going to do for now is just graph a few points. We're not going to try to graph the whole graph, but there are many more points on the graph. And there are lots of points that are not on the graph, so we can also do that. So meanwhile, for example, 2, 4 is not on the graph. So I would not draw a dot there. So pretend I go over to 2 and then up 4, which is right there. I just did what I'm not supposed to do. It's not on the graph, so I would not actually draw that. I'll just leave it alone. So I don't draw anything if it's not on the graph. And how do I know this is not on the graph? Well, it's because x equals 2 is not assigned by the equation to y equals 4. If I plug in x equals 2, I will not get that y equals 4. Because I already know if I plug in 2, I'll get y equals -1, and that's it. We already tested that. There was no other option. So there's lots of points that are not on the graph too. And I can, in fact, I can just verify it real quick. If I try to plug it in, so I replace x with 2, and I replace y with 4. So let me write the whole thing down. So here's how I can test that this is not on the graph. So you can check this. Oh, my library book is due soon. We can check this by plugging in both x equals 2 and y equals 4 at the same time and seeing if the equation holds true. So let's see what that means. So I'm going to take my equation and I want to see if 2 comma 4 is on there. It's on the graph. So what I'm going to do is I'm going to change the x to 2. I'm going to change the y to 4, aka plug those numbers in and see what I get. So I get that 6 plus 4. Does that equal 5? Does 10 equal 5? No. So that tells me exactly what I want to know, that 2 comma 4 is not on the graph because x equals 2, y equals 4 does not satisfy. There's one way to say it, does not satisfy the equation. And that's all there is to that. Okay. So let's do another example using our other equation that we already sort of worked with a bit. The equation x plus y squared equals 6 has 2 points for sure on the graph. If you check your work from earlier in these notes, it's got to have 5 comma 1 and 5 comma negative 1, because earlier we already showed that this assignment happens. If I plug in x for 5, I'll get 1, but I'll also get negative 1. So I have this sort of double arrow coming out of 5 if I draw it in this way. X is turning into both 1 and negative 1, and that's what we showed earlier. And so if I want to draw these 2 points, I can. So this would be 5 comma 1 and 5 comma negative 1. These are both on the graph. But for example, 0 comma negative 2 is not. Again, same thing as before, because if I take my x plus y squared equals 6 equation and I use x equals 0, y equals negative 2, I'll get 0 plus negative 2 squared equals 6. Is this true? No, negative 2 squared is 4, because again, the negatives will cancel, and I'll get 4 equals 6. No. So that's why this is not on the graph. Okay, so then just to quickly summarize, we can find points on the graph just by picking any x value that we want, like we did before, like we picked 2 or 1 or 5, I think. We can pick whatever we want, then solving for y values that the x value corresponds to. And those points will be on the graph. And we can check if we just have a point already. You can check if it's on the graph by simply plugging in x and y. So by plugging in x and y and seeing if the equation holds true or is satisfied, however you'd like to put it. Okay, so one more example with a slightly more complicated equation. So let's find the point on the graph of, so here's my equation, x squared minus 2x plus 4, a little bit more complicated than before, corresponding to x equals -3. So here, x has already been decided for us. We just want to find the point that goes with that x value. And the interesting thing about this equation is that y has been solved for, meaning I got everything else to the other side. And that's a very useful thing that we're going to see a lot. Okay, but in any case, all we got to do is replace x with -3 to see the corresponding y value that it's assigned to. And go from there. Okay, so replacing x with -3, aka plugging in -3, aka setting x equal -3, just means change all your x's to -3. You just literally just copy paste. And then you put parentheses around it so you're very careful. And then afterwards you deal with the order of operations and the math stuff that might seem confusing to you, but just do the first step first like this, and then you can't go wrong there. You can only go wrong on the next steps. Okay, but you just progress slowly. So what's -3 squared? That just means do -3 times -3. Well, the negatives will cancel. 3 times 3 is 9. -2 times -3, negatives will cancel. 2 times 3 is 6. And now I just have to add 3 numbers together. This will be 19. So what's the point on the graph corresponding to x equals -3? It's -3 comma 19. And it's again because -3 is getting assigned to 19 by this assignment that the equation creates. Okay. So this equation is a bit nice because, like I said, y has already been solved for. And so it'll do something interesting. This equation will always turn an x value into just one y value. So notice how -3 got turned into 19, and that's it. It didn't get turned into anything else, just 19. That's different than the previous example where 5 got turned into 2 different things. So as opposed to x plus y squared equals 6, which assigns x equals 5 to 2 things, to both y equals 1 and y equals -1 at the same time. So in our little chart, it looks a bit weird because 5 has got 2 arrows coming out of it if I draw the same sort of thing. And what we are interested in is the case like this example, where this happens, when the equation will always turn an x value into just one y value. Those are the things we like. Okay, so an equation with this property is called, instead of just being a mere equation, now it's called a function. It's somehow this like extra special equation that's way better than other equations. So it gets its own name. It's called a function. And you can say it a little bit better. You can say something like y is a function of x, because the y values are being determined by x. So you think of it as this little machine that turns x's into y's in a nice way. It never turns one x into two different y's. You never want that when you have a function. It's much better. It always turns one x into one y like this. It's a little machine that does that. So it's good to visualize it like that. So you think of functions as little machines like this. They turn one number into another number. One number goes in, called x, and then one number pops out. But an equation doesn't necessarily have to do that unless it's extra special. And then it's a function. Okay, so for example, negative 3x plus 4y equals 2 is another. So here, y is a function of x because, so it doesn't look like this one did, where all the other stuff was on one side. And you might think that that was the giveaway that this is a function and not just any old equation. But what we can do is we could rewrite this other one in that same way. So it's a function because you can solve for y in a nice way. So in a way that reveals. So just because you can solve for y doesn't always mean it's a function, but if you can solve for y, then you can reveal if it's a function or not as you do that. Okay, so we're going to solve this equation for y here. So I'm going to just add 3x to both sides. To get started. And then I can get y alone. I can completely get it alone by dividing by 4 on both sides. So this is an algebra step you may not remember very well. So I can divide by 4 there and there. And what happens is 4 divided by 4 is 1. So that just becomes y on the left. And it's okay to do it as long as I'm doing it to both sides, which is why I've done this step. But now on the right-hand side, I can split this fraction up as 2 over 4 plus 3x over 4, if you like. Either way is fine. And you could even put, people like to write the stuff with x in front usually, so maybe they might write it as 3 over 4x plus 2 over 4 instead. But the point is, I can get y alone, and I can reduce fractions as well if I like. So 2 over 4 is 1/2. That's fine too. So this reveals that y is a function of x because now I can see that anytime I plug in x, I'll just get one value of y popping out. So now we can see that a choice of x becomes only one y value. So as soon as I pick x, if I pick x to be 10, then the little machine will say, okay, do 10 times 3/4, then add 1/2, and that'll tell you y. And there's no duplication going on, so I'm only going to get one y value. There's no two choices ever happening, no matter what number I start with. So that's why we can say for sure that this is a function. So the times you're not going to have a function are when you start seeing y's with powers, or that's pretty much the only stuff you're gonna have to deal with. But we'll worry about that later. Okay. So this reveals that y is a function of x just by solving for y. And then you can look at it and you can just see that if I plug in x values, I'm only going to get one y value each. So x equals 10 will turn into y equals something. X equals 11 will turn into y equals something. You can calculate it if you like. It's a bit annoying with these fractions, but the point is you never have one x becoming two different y's. And that's what you don't want. Okay. So this situation not happening to be a function also means something about the graph. So this also means the graph of a function as opposed to the graph of an equation, they're both just the x, y coordinates that work that you get by using the equation or the function, but the graph of a function can never have two points with the same x value. And why is that? It's because if 2 points had the same x value, that would mean you're in this situation here, which would mean it's not a function. So let's see some examples of this situation. So if the graph, so for now, I'm just going to draw dots. So if these points came from the equation, then that equation could be a function. So if this graph, or if these points came from an equation, it could be a function. And that's because there are no points, these are all the points, with the same x value. So this one is 3 comma something. This one is 2 comma something. This one is 1 comma something. -1 comma something. -2 comma something. -3 comma something. I'm not worrying about a y coordinate that's assigned to it from the x coordinate, because all I'm seeing is if any two have the same x value. And they do not. So what that means is there's been no situation where, like we saw with x plus y squared equals 6 a long time ago. There's no situation like over here where 5 got turned into two different things. That is not happening here. So we're good to go. This could be a function. Whereas this is most definitely not a function because of this exact situation here. But typically our graphs are going to look like curvy lines. They're not going to just look like points separated out like that. So something you're more likely to see is something a bit more like this. So this is a full graph. It's not just some points that you checked. This is a graph where you know the entire shape, and we haven't done things like this yet, but we will eventually. But right now what we can do is we can look at it and we can see, we can ask, could this be the graph of a function? The answer to this one is yes. It's again because there are no x values. So if I go across the x-axis in both directions, there's no situation where a point on the graph, like this guy here, shares an x value with another point. Because if it did, it would have to be right above it, something like this. But those points are not on the graph because they're not on this line that I've drawn. And this never happens anywhere, no matter where you go. There's no points above it or below it vertically. And that's really all we have to check. So what we do is we sort of think about this imaginary vertical line going across the graph. We pass it along the graph and we see if it ever touches the graph twice at the same time. And it never will in this situation. It'll just keep hitting it once because there are no points vertically above it themselves or other points on the graph. So this is called the vertical line test. So what we say is we say it passes the vertical line test. Now it's easier to see how this works when you see something that's not a function to compare it to. So let's do that next. So something like this. This is not a function. And that's because it's got a situation like this. It's got many situations like this, but one is enough. Here we have 3 points, the same x value. So the point is that they are just vertically above each other. And so if I were passing my vertical line across this graph, doing this vertical line test, as it eventually got over here, I would see that I keep getting situations where there are points on top of each other, above and below each other. And that tells me that whatever equation created this, so whichever equation created these points has the situation where there are x values. So we can just pretend, let's say this is like -1, x equals -1 there. So here we have like -1 being assigned to 3 different things. So that would be like -1, 0, because there's no y value. This might be like -1, 3, and this might be like -1, -2. So this is saying that -1 is getting turned into 0, 3, and -2. So whatever is doing this, even though I don't have the equation to look at, just by looking at the picture, I can say for sure, because this vertical line situation is happening, that this is definitely not a function. So this type of picture is the main idea between for seeing like when an equation is a function or not, when you don't actually have the equation on hand and all you have is the graph. So we can sort of do these very quickly now. So something like this is a function because if I pass this imaginary line down, it'll never touch the graph above or below itself anywhere. It'll just go straight across, only ever touching it once at a time. So this yes is the graph of a function. But something like this, a circle, is not, because if I do the vertical line test, I pass the line across to the right here, I will end up with a situation where it touches the circle, the shape twice, where 2 points are above or below each other. So this is not a function. Okay. So again, what's really going on is we have something like -2 here for x getting turned into 2 y values if you draw the little chart. Okay. So just to take it back to the original bad example of something that's not a function, we saw that x plus y squared equals 6 has both 5, -1 and 5, 1 as points. And using our vertical line test, even though I don't have all the points graphed, I just have 2, I can already see that this is not a function. So this is revealing this is not a function, even though we haven't graphed the whole thing, just 2 points. You can already see it with just 2 points. Okay. So then what can we do with functions? So we can draw them. They pass the vertical line test. What else can we do? So when an equation is a function, we can write it or rewrite it can always do this. If it is a function, y equals, and then I'll just say x stuff. Basically, we can get y on one side using algebra and everything else on the other side by solving for y. This will always be doable if it's a function. So for example, x squared plus y equals 2 is a function, so I should be able to solve it for y. All I have to do is subtract x squared on both sides to get y equals 2 minus x squared, or people like to write the x stuff first, -x squared plus 2. Either way is fine. So then what we do is we use something called function notation. So a lot of material in this first lecture, but we'll narrow our focus more next lecture. So next we use function notation, and it's just a different way of writing sort of what we've already been doing anyway, just because we like to confuse people more, so we give them more and more notation all at once, unfortunately. So what we do is we write y equals f of x instead. And f of x is just sort of a placeholder for all this stuff. That I mentioned before, stuff with x. So in this example, we might just write y equals negative x squared plus 2 as f of x equals negative x squared plus 2. Or you could even just write all of it, f of x equals negative x squared plus 2. So the purpose of this is to really hammer home how y depends on x. So it really is a function of x. And so what we're doing is we've named the function something. Instead of just saying the function, we name the function something. Usually it's f, g, or h. In this case, it's f. Whatever happens to be there is the name of the function. And it depends on x. And that's what this is saying. Okay, so we're going to use this notation a lot. So it'll be a lot easier once we just get familiar with using it. Okay, so then to find where x values are assigned, like we were doing before, plugging in x, seeing what y was, or points on the graph. So that's just seeing where x goes and then writing it as a point like we did before. So to do this stuff, you can sort of do it a little bit more easily with this notation. We write things like this. F, and this is saying, the way you say this is you say f of, and then you just put the x value that you want to see where it's assigned in the parentheses. So for example, if I put a 5 here, this really means the y value that x equals 5 is assigned to. And then we can find it like before, except it just looks a bit funny now. So for example, if y equals negative x squared plus 2, like above, then we write with our fancy new notation that f of x equals negative x squared plus 2. We're not really doing anything. We're just changing the name. And then if I want to know where 5 is assigned to, this just means what we were doing before. It means change all x's to 5s. But that's what we were doing before. That's what plugging into the equation was. But it's just a different way of doing it, a different notation. So this is just saying change all the x's to 5s. So 5 squared is 25, but the negative's on the outside, so it's still negative there. Negative 25 plus 2 is negative 23. So before we might have written something like this. 5 got sent to negative 23. Now all that's different is we've named this function f, so you might draw a little f there in this notation. But it's really the same process as before. I'm just changing my x variable to 5 and solving for y, except I'm not calling it y, I'm calling it f of 5. Until the end, I change it back to y. And then I figure out that it's negative 23. And it still means 5 comma negative 23 is on the graph. But now you have a name for the function, so you say it's on the graph of f. Okay, so the main aspect of this lesson is really just getting familiar with this function notation. So it took a long way to get there, but this is really the goal of today. So what we can do is we can create functions without ever mentioning equations now. So we don't have to reference equations at all. So equations are kind of a hassle to work with because you got to constantly worry about if they're a function or not. So what we just do is we just start with a function directly by writing something like this. So now I've created a different name. This function is called g. So it means the function is named g instead. And now I can do the same type of stuff. So I can like determine the y value that g assigns to x equals -4, just like before, but now what this really means is just figure out g of -4, meaning plug in -4 for all the x's. So that's what I've done. I've just changed all my x's to -4s. And that's how we do this step here. And then I worry about algebra after. So -2 times -4 is +8. That becomes 18. So the y value is 18 that x equals -4 is assigned to. Okay. Let's just keep practicing. So if h of x, so I can name it h instead of f or g, it's another common choice. So here's x squared divided by 4 minus 2x plus 5. And I could just immediately say something like find h of -2. Okay, a little bit quicker now. It's just this. This just means, once again, replace x with -2. And then the result is y. So I'm just going to replace x with -2. And unless I'm very comfortable with algebra, I'm not going to try to skip too many steps when I do it. I'm just going to do it very literally, copy paste. And then I'll simplify it a little bit at a time. So -2 squared up top, that's just going to be 4 because negatives cancel. Then 2 times 2 is 4. -2 times -2 here is also 4. Then I got this 5 hanging out. These 4 cancel. 4 divided by 4 is 1. And so this adds up to 10. So the assignment of the function is that x equals -2 is getting turned into y equals 10. It's one way to think about it, except I never mention the y variable until the end with this fancy notation. So it's just a little bit quicker and easier to work with than a whole equation. And it still means the same stuff as before, so it means -2, 10 is on the graph of h. Okay. So one very last thing to notice. This video seems like it's very long. We shall see. One thing I want to mention is we can immediately conclude that -2, 11 is not on the graph. Just because I already know this one is, so why do I know this one's not? It's because it's a function. There are no x values that get turned into 2 y values. So it would mean if it was on the graph, that -2 is becoming both 10 and 11, but functions don't do this. So that's why I know this is definitely not on the graph, because I already know that the first one is. -2 can only turn into one number. It's already turning into 10, so it can't turn into 11. So this means we could do problems like this very quickly. I can find, my hair keeps getting in my eye, it's too long. Find 2 points on the graph of a function, something like this, and 2 points not on the graph very quickly. So if I want to find 2 points on the graph, I just have to pick 2 very convenient numbers for x, and that'll get me 2 points. So let's do that first. 2 points on the graph. So I should make my life easy. I'll pick 2 easy numbers for x. 0 is a nice, friendly, easy number. And x equals 1 is another friendly number to work with. So f of 0 is what I'm looking for. That means I'm changing all my x's to zeros. There's only one x to change. I just do it there. 0 squared is 0. 3 times 0 is still 0. 0 minus 4 is minus 4. So I know 0, -4 is on the graph. But then I immediately know something that's not on the graph. 0, -5. And I need 2 that are not on the graph. So how about 0, -6 also? That's because this is a function. So once I know one x value goes to -4, I know it can't go anywhere else. So it can't go to -5, it can't go to -6. So those 2 I can say are definitely not on the graph. Okay, and then one more on the graph. I just have to plug in 1. Other number, conveniently, I'll choose 1 because it's not so bad to work with. 1 squared is 1. -3 times 1 is still -3. -3 minus 4 is -7. So 1 comma -7 is another one that's on the graph. Okay, so next time we will narrow our focus down to one specific type of function. And that's it for today. See you next time.